in
Hello,
two
everybody,
different
and welcome to
directions.
Climate Change
And of
Day
course,
3.
now as it's
Last
going
time
along,
we were
it's getting
together, we
little
took a
bit
look
muddier
at the layers of
and
the
harder to
atmosphere,
see,
and we
but
saw
I
how they
think
were
that you
separated
get
by
the point.
atmospheric movement. We also learned that all of the weather that we experience on a day-to-day basis takes place in the troposphere. So today, we're going to dig into the troposphere and learn a little bit about how air circulates within it and how that helps move energy along. So come on, we're going to learn about weather. Our quote from today comes from journalist and environmental activist Bill McKibben, who says, in reality, climate change is actually the biggest thing that's going on every single day. And in his book, Earth, with 2 A's, we see what life is like on a planet that is very similar to our own, with the only differences being that the climate is changed a little bit. We have this in the BCA MSc library, and it is a very good read. So if it's going to be your turn to do your current event, be ready for it. And next, we're going to jump into a little lab activity. It's in 3 parts. We're going to do them here, and while we do these here, you should go ahead and take the packet that's on your Google Classroom page and go along as we do it. That might mean that you are pausing the video as we go so you can record stuff, and that's quite all right. You can pause and push play as many times as you like. Okay, so the first thing we're going to do is we're going to come on over to our little lab area where we've got a little model of the troposphere built up. And so I have here the area of our atmosphere where we do have mixing occur, the troposphere, and it is in this baking dish. And the bottom of the baking dish is representing the surface of the Earth, and the top of the baking dish is representing the top of the troposphere known as the tropopause. As you can see, at one end of the dish, we have some candles that are sitting below it, and those are going to represent the equator, an area of a lot of heat and a lot of energy. And at the other end of the dish, we've got a bag of ice. And so you can tell that this is representing the regions from the equator up to the poles, and we have one of those ends being devoid or reduced in the amount of energy that's present, and one end that has an abundance of it. And so I've got some food coloring, and we're going to use that to trace the movement of air through our troposphere as we're having interactions between our energy-rich equator and our energy-poor poles. And I've got 2 colors. The only reason we're using 2 colors is just so you can see where things came from. I'm going to place the red food coloring in at the equator, because I think the equator is being hot, and I'm going to place the blue food coloring in the dish by the poles. I'm going to try to put in one drop. I'm going to try to do it at the same time. Probably won't get it exactly the same, but we'll do our best here. Okay. Oh, and you probably want to see that a little better, so I'm going to put a piece of paper underneath here for you, so you can see what's going on. That might make things a little bit better. And as we do this, we can see that the blue has sunk to the bottom, got a little bit still on the surface, grabbing a hold near the ice. But the red has lifted up, it's spread out, but is mostly traveling along the top of the water, along the tropopause, away from the equator and towards the pole. And as we can see, as it's traveling farther away, some of it is falling back down. And as it's falling back down, it's moving back towards the equator. And so we've got these 2 masses of fluids that are traveling in opposite directions, one above the other. The red is traveling away from the equator towards the poles, high up in the atmosphere, at the up near the tropopause, and we've got that cold polar air traveling back towards the equator along the surface. And I think that shows a good representation of how we're moving energy.
So where does energy from the equator go? Well, energy that reaches the surface of the Earth at the equator travels up and then out towards the poles. What happens with cold air that's near the poles? Well, it sinks and it travels towards along the surface back towards the energy-rich regions of the Earth.
Every time I do this, I think it's like the coolest thing to watch. You can actually see in one container of water, we've got flow moving in two different directions. And of course, now as it's gone along, it's getting a little bit muddier and harder to see. But I think that you get the point. Okay. So you do not need to watch the video of us doing this a couple of years ago because you just saw us do it live. Now, our next activity takes this and combines it with the fact that the Earth does not just sit still, but it rotates. And so if we want to understand how the rotation of the Earth plays into these moving air currents that are moving between the equator and the poles, we need to take a different look. And I've got just a thing to show you how the Earth can spin. And this is a grand adventure over here. I'm putting these back on not because we particularly need them for spinning the stool, because I am next to the glass that does have flames underneath it. And what I have here is I have a stool that can spin, and I'm going to take my circle of paper, and this circle of paper is going to represent a top-down view of the Earth. So I can put a dot in the middle, and that dot in the middle is going to represent the North Pole. It could represent the South Pole, but we are looking down, so it's going to represent the North Pole. And the edge going around is going to represent the equator. Now, I'm just going to tape this using some tape. I know it's tape because somebody wrote tape on it. I'm going to tape it to the stool so that way it stays put throughout this activity. Just use two pieces of tape. And if I wanted to take the shortest trip from the pole to the equator, I would just go straight there. So I would take a ruler and I would put it here, and I'm going to draw from the pole to the equator. Essentially, we're making a radius of this circle. And straight there, and I'm going to label this number 1. That way you can see it. Now, of course, you can't actually do that because the Earth doesn't just sit still. The Earth spins. And so as we spin the Earth, we're spinning it this way because the Earth, as you look down from the top, does rotate around its axis counterclockwise, which we know because the sun rises in the east. And if I now, while this is spinning, were to do the same thing, and I've got to do it without the ruler this time, please forgive me because I have to spin the Earth with my right hand. If I'm to draw a straight line, I'm just going to draw straight towards myself. While it's spinning, we're going to see what our line looks like then. So I'm going to see if I can get self-centered. Okay, so we did it. Right. I should label this number 2, so that way you know this is the second one that I drew. Number 2. Okay, so let's take a look. We have our first one, which is a straight line, but even though I drew the line perfectly straight, or as close to perfectly straight as I can, I just pulled the marker directly towards me, the line that resulted came out curved. And that's going to be really important for us as we look at prevailing winds on Earth. So let's head back over to our main station, and we will take a little bit of a look at a video that should help us kind of understand what's going on here.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
Right, here's the game, right? You're going to throw the ball straight to what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it, all right?
Yeah.
Right, what's going to happen, dude?
That's going to veer off to the left.
So the ball is going to swerve off to the left,
Yep.
and you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, so everyone, no, hang on, one more.
He's not arrogant.
Just quietly
He's not
confident.
catching it. He's not
Really?
catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got 1 second to go off to you, 1 second comes to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round. But where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
Right, in your own time, throw the ball.
I got this.
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
Right.
Yeah, I did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, it curved right in.
Right, so we all agree here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
No idea. It's called the Coriolis Effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to, and that, ladies and gentlemen, is a Coriolis effect.
Okay. So, let's come on back. So what's going on here? There we go. So, this Coriolis effect has a lot of implications for us because as air is traveling through the atmosphere along the surface, it is going to travel straight. But because the Earth is spinning beneath it, it is going to make that air appear to bend. And because it makes the air appear to bend, we get winds that do not just travel north and south between the equator and the poles. We get winds that travel with an angular direction that has an east or a west component, depending on if the air is traveling on the ground towards the pole or towards the equator. Now, that's weird because we just saw that air travels on the ground towards the equator and along the top of the troposphere towards the pole. So, what's going on? Well, it turns out that as you were watching that, you could see that hot air, not all of it was making it towards the pole, that it started sinking as it was cooling. And in real life, essentially none of that air actually makes it all the way. As that air travels north, high up in the atmosphere, it cools down and it's going to sink. And that air is going to sink before it gets to the North Pole. In fact, it'll happen somewhere around 30 degrees north. And so you end up getting a circulation cell that happens here, where you have 30 degrees north, serving as kind of like the pole, because there's not enough energy to keep that air going. Now, because we have heating happening not just at the equator, but all the way up, you end up getting a series of circulation cells happening both in the northern and southern hemispheres. So we can see that at the pole, at the equator, warm air is rising, and it's traveling at the top of the troposphere until it cools down. And when it cools, it condenses and it falls towards the surface of the Earth. And once it gets there, it gets pulled back towards the equator. Now, we also have warmth hitting the ground in other regions as well. And as we've got this sinking, not all the air that comes down goes to the equator. Some of it travels north along the ground in what's called the Ferrel cell until we get to about 60 degrees north, where it will rise again. And when it rises again, it's going to head south along that tropopause toward the middle latitudes. And you've got a polar cell as well. And at the top of the world, where you have that rising air at about 60 degrees north, traveling up along the top of the troposphere until we get near the pole, where it will sink and flow back down. So this difference in temperature causes these circulation cells, your Hadley cell, your Ferrel cell, and your polar cell. And then the rotation of the Earth, where we've got this north-south component, causes the prevailing winds. So here, between 30 degrees north and the equator, air is traveling south along the ground. And as it's traveling south along the ground, it's getting deflected to the west. And so here, you end up having your trade winds, your prevailing winds, coming out of the northeast. Whereas if we go up north to the latitudes where we live, we are seeing that as the air is traveling north along the ground from the south towards the north, so from about 30 degrees north and from about 60 degrees north, as the Earth is spinning in that Ferrel cell, those surface winds are being deflected towards the east. And so we end up having our winds coming from the southwest, prevailing winds. So of course, there are other features that cause us to have days where winds come from other directions. And then, if you go farther north, again, you get that same effect that you had down in the Hadley cell, down in the tropics. You get the polar easterlies, which are coming from the northeast. One thing that you should also notice is that in that video, the deflection did not appear to be straight or be perfectly evenly curved. It appeared to go straight for a while and then deflect. The faster you are changing your rotational speed, the more of a deflection you are going to get. And so as we travel north from the equator to the pole, the Earth is getting the circumference of that latitude line is decreasing at an increasing rate, and so we're getting smaller and smaller, faster and faster. And so that's causing more and more deflection the farther away from the equator that we go. This phenomenon causes us to get ocean currents as well, whereas we have these driving westerlies up in these regions up here, kind of near the top edge of our Atlantic and Pacific ocean basins, and then along the southern border of the North Atlantic and the southern border of the North Pacific, we've got winds blowing from east to west. Well, if we've got motion going like this in those two areas, that water that's being pushed by those winds has to go somewhere, and it's going to circle. So as, let's say, look in the North Atlantic, as the water that's being blown by the wind reaches Europe, it has to go somewhere. And where does it go? It turns south, because as we go down along the coast of Africa, well, the wind was blowing that water away, and we needed water to come back and fill that space. And so you end up getting ocean circulation or ocean gyres. Not only does this current move water in this circular fashion, but it also moves a lot of energy. we have a lot of energy that's stored in the water here. It's a lot warmer. And so if we look at this current, this is the Gulf Stream. As we go north in here, the wind is blowing that warm water north and then east. And so we're bringing warm water to Europe. And so if we look at areas at the same latitude that are not as impacted by the Gulf Stream, say in Labrador, at the same latitude in Labrador, Canada as the UK, we find Labrador to be much cooler. So these ocean currents, these gyres, this circulation of water and energy is very important for how we experience climate differently in different parts of the world. If the Gulf Stream stopped or became weakened and we brought less warm water to Europe, we would have a different experience there. Would it cause it to cool down a little bit? Would we get an ice age in Europe? These are some very important questions for us to be able to answer. Not related to climate, but one impact of us having these circulating ocean gyres is because of the forces involved. When you drop trash into one of these gyres, it tends to get pulled towards the middle and stay there. And this is what causes the phenomenon of the Great Pacific Garbage Patch. We also have a similar, although less well-known phenomenon in the Atlantic, where we also trap seaweed in a gyre called Sargasso. And so we have the Sargasso Sea. It's an area in the middle of the Atlantic over here, where you see a lot of seaweed floating around. So that's kind of the deal with our prevailing winds on Earth. They're the result of both the uneven distribution of temperature and therefore energy between the equator and the poles, as well as the rotation of the Earth. That takes care of wind, but that's not the only thing that gets impacted by this as well. We also have precipitation. You know that at 10 degrees north latitude, we have tropical rainforests, but at 30 degrees north latitude, we have deserts. And that's not by chance. Let's take a look at this again. What's happening here? Well, we have a lot of energy. We're evaporating water. As that water evaporates, it goes up, and it travels with the air along the top of the troposphere. And what happens up here? It gets cold. And you know water vapor, when it gets cold, condenses into liquid water, and it rains. And so by the time we get to the edge between the Hadley cell and the Ferrel cell, we are essentially devoid of water vapor. So as we get this high pressure zone, as we are pushing down, this air is sinking, there is not a lot of water vapor, and we tend to get really dry conditions. And so where on Earth do you see deserts? Well, you see deserts at about 30 degrees north and about 30 degrees south. You see deserts in Chile, you see deserts in the United States. If you go into Asia, you see deserts in areas about 30 degrees north in Mongolia, and about 30 degrees south, you see deserts in Australia. If we go a little bit farther north, we're seeing the same phenomenon as we were seeing at the equator, where we are having air rising, warm air rising in the temperate latitudes. Well, we see more precipitation there as well. And so if we look at where we are, we tend to see a lot of precipitation in kind of this band right around here. Why? Because as that air rises and starts to travel south or north, it cools down, it condenses, and then it rains. In which that causes us to have forests in these areas. We have what we can call temperate rainforests in some areas, and we have boreal forests or temperate deciduous forests if we go a little bit farther east. Based off of that, would you expect there to be a lot of precipitation or a little precipitation at the poles? Well, you'd expect little. Why? because what's happening there? Well, we've got that air with a high pressure falling, and that air is devoid of water vapor. And so on the poles, even though it's very cold, you don't end up getting a lot of snow precipitation because there's not a lot of vapor in the atmosphere. So, your take-home message. As weather patterns become more intense, so as we have more energy reaching the equator, we will have a greater temperature difference between the equator and the poles, or a greater energy difference, which will cause these circulation patterns to become more intense. And as these become more intense, we get more evaporation at the equator and in this temperate latitude where we live. And when we get that, we will have more rain in the rainy regions. But as it becomes more intense, we also get less rain in the drier regions. So, as the weather patterns become more intense, the wet latitudes will become wetter and the dry latitudes become drier. This is how, with climate change, we can get both more flooding and more drought. It's spatially separated. So that's kind of our big message for today. So, I hope you had a good class. Make sure that you come to class, you've finished up taking your notes on those activities, and you're ready to discuss global precipitation and wind patterns. Have a good day, everybody. Bye-bye.